All right, electric charges can do some pretty crazy things. And one thing that was done was an experiment where the scientists took a charged sphere, like we used in class, and put a charge on it. So it's got a bunch of negative charges all over it. And then they took another object, okay, let's say a smaller sphere, and they also put a bunch of negative charges on it. Okay, so you know that these things are going to repel each other. And what they did was they made this little object actually levitate. It actually floated there in space. So here's how they did it. Okay, let's say we have, first of all, this is a repulsive force. Okay. First thing we're going to need to be able to do is draw a free body diagram to represent that. So we know this is not accelerating up or down. So it's got equal vectors on both sides. You got weight pulling down, then you got the repulsive electrical force pushing up. Now, because these have to be equal for this not to accelerate, we can also say that electrical force equals the weight. Okay, let's apply some numbers here. That sphere, let's say, has a charge of -6 microcoulombs. Okay, let's say we don't know the charge of this. Okay, that's the question mark. Okay, let's say the mass of that, the top one, is 0.2, let's say 0.2, let's go 0.2 grams, which is like 0.002 kilograms. Actually, 0.0002 kilograms. Okay, let's also say that the distance here, the radius, is like 1.6 meters. So my question to you would be like, can you find the charge on this little sphere here to cause it to float? Yeah, sure you can. So we know that the electrical force is equal to mass times gravity. So I'm going to bring this right down here. So electrical force equals mg. Okay, we also know that the electrical force is equal to K Q1 Q2 over R squared. Okay, we know that that's equal to that. Equals the mass, which is 0.0002 kilograms, times gravity. Okay, we also know that. Okay, so let's clean it up just a little bit. Let's solve for this side, and then go ahead and try to solve for this side. Okay, so K is 9. Q1, okay, we gave a charge of -6 times 10 to the -6 coulombs. Q2, we don't know. Radius squared, 1.6 squared, equals. And then we do the multiplication here, okay, which would be 0.0002 times 9.8. Okay, this is 1.96 times 10 to the -3rd on this side. So again, we're solving for the charge on that tiny object there. Right, so let's do some math. So after typing away on the calculator, on the left side here, what I've got is 8239.7 Q2 equals 1.96 times 10 to the -3rd. Okay, so I'm going to go ahead and I'm going to divide. And get 2.37 times 10 to the negative 7th coulombs. Okay, there's my answer there. All right, so that little object there has to carry this much negative charge in order to float there. Now, what I'm going to do is I'm going to bring that a step further. Okay, going to bring that a step further. So if I look over here, okay, 2.37 times 10 to the negative 7th coulombs is the charge on that. So my question to you would be, how many electrons, extra electrons, are sitting on the surface? Okay, and that's pretty cool to know that you can get the number of electrons on that surface. So all it is here is a simple conversion. So I'm going from charge to number of electrons. So I've got my big number here, well, a small number actually, 37 E negative 7 coulombs. Okay, and now I'm going to find out how many electrons are in there. So I'm going to have to divide out by coulombs. I know that the charge of an electron, one electron, has a charge of negative 1.6 to the negative 19th coulombs. So I can go through and I can figure out by dividing these two how many electrons there are on that surface, which I think is pretty cool. And after doing the division, I found out that there are, I'll write it a little neater, 1.49 times 10 to the 12th electrons on that surface. That's pretty cool. Yeah, I can actually write that as a big number to show you what that looks like. So 1.49 times 10 to the 12th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 149,000,000,000,000,000. Okay. There are this many electrons on that little tiny surface there. Cool stuff. And if we actually touch them together, we can get them to ground out and go back into the ground and then reduce that down to no free electrons in a split second. So they move pretty quick. All right, that's an extended example, and you'll need that to work out a couple of the problems.